This is Mr. Hardesty. We'll use synthetic substitution to find the zeros for a given polynomial equation. Find all of the zeros of g of x equals x to the fourth plus x cubed plus 3x squared plus 5x minus 10. Our given function is to the fourth degree. X to the fourth leads the way, which means we should find 4 zeros. To find our first zero, we will guess at what would be a reasonable zero to get us started. If you have a graphing calculator, the best way would be to load that function into the graphing calculator so you know one exactly. But we'll guess and use some synthetic substitution to get us started. Let's try -1. We'll list the coefficients 1, 1, 3, 5, and -10, and do our synthetic division. We'll bring down 1, multiply, and get -1, add our column and get 0, multiply and get 0, add our column and get 3, multiply and get -3, add and get 2, multiply and get -2, add and get -12. Since we have a remainder, we know that -1 is not one of the zeros. Let's try +1. And we'll list all our coefficients. We'll bring down 1 and multiply and add to the corner. 1 times 1 is 1, add the column, 2. Multiply 1 times 2 is 2, add the column, 5. Multiply 5, add the column, 10. Multiply 1 times 10 and get 10, add the column and get 0. This is good news. This means 1 is one of our 4 zeros, and we need to find 3 more. That 1 can now be represented as a factor, and as a factor, we'll write that as x minus 1. Our remaining factors will come from our depressed polynomial, which we can represent now as 1x cubed. Remember, the original was quartic to the fourth, so we're now down to 1x cubed, plus 2x squared, plus 5x, plus 10. This is cubic, so we should get 3 zeros out of this, and we'll do that by factoring. Let's factor by grouping. We'll group the first 2 and the last 2. Out of the first 2, the common factor is x squared, leaving us x plus 2. And out of the second pair, we take out 5, and that also leaves us x plus 2. So this has worked great for factoring by grouping. We'll bring x squared and 5 together as one binomial factor times x plus 2. Now if we go back and include x minus 1, we have factored that original quartic, and we'll set it equal to 0 and solve for all of our roots. The zero product property will say if you multiply these 3 factors together and get 0, one of them has to be set equal to 0. Well, the first one we've already taken care of, but we'll show that again. We'll add 1, so one of the roots, one of the zeros, is 1. Set x squared plus 5 equal to 0 and solve. Subtract 5 from both sides. X squared equals -5. And to make x squared just x, we need to take the square root of both sides, which is going to leave us positive or negative. I will come out for our negative. 5 stays in the radical. So there are 2 more roots, and they're both imaginary. Finally, x plus 2 equals 0. All we have to do here is subtract 2. So x is negative 2. We'll recap the whole thing. As I started, our roots are zeros at the beginning. 1, negative 2, and then positive or negative I radical 5. There are the 4 zeros to the original quartic function.